Hi, thank you all. I want to talk a bit about something a little different, running petrochemical and running those things a little bit otherwise. This is in the mining sector, direct iron reduction furnace. We've used Cape Town to try and put together a flow sheet, at least the first draft of the flow sheet, put this way. So in the iron industry, they're obviously trying to get rid of the CO2 footprint, and there's some numbers. We can see the iron being produced, and you can see the CO2 footprint over time, and some 25% of industrial emissions, in terms of CO2 emissions. And you can save by making steel more efficient, making it thinner. Cars become the body works thinner. You can get more mileage out of it. But in the end, at some point, you need to make a big change in the process, and this is what has led to this idea. Instead of using the classical CO, use some reactions down there. Classical carbon monoxide, which you can get from a reform or something like that. You use hydrogen, which you then get from electrolyzers and so on, the green hydrogen footprint. So now our research department, we have a whole group, the HYSA group, which studies the whole hydrogen cycle, hydrogen production, the fuel cells, and so on. And they're basically interested in some kind of techno-economic study of using, instead of using CO, to use hydrogen in a DRI furnace. So what happens here is you have iron ore pellets, they're about the size, 10 millimeters or thereabouts in size. They are dropped into a furnace from the top, and then you have hydrogen rises up through some counter-current fixed bed type arrangement. That's how it functions. And then there are many reactions actually which occur. There's in fact 3 reactions, the 4 reactions which occur. All the reaction steps are endothermic. The ones in green are the ones with hydrogen. They're endothermic. They require energy. And this is the overall reaction step. The iron hematite, as they call it, goes to pure iron and releases water. Right. So the objective then is to get some kind of model for this process. Okay. So the first part of the story is to look at the pellet, and there's of course the simplified first principles approximation we all learn in lectures, but let me just show you some pictures about the iron materials and some of the literature or some of the models that are currently out there, and to justify why I've kept it simple. This is an iron pellet. You can see the different layers. The core is the hematite, that one over there, and the outside shell would be the iron. And there's some gradient which is present in the iron. And under certain conditions, this is what happens. And there are many models in literature which try and look at the layered approach. And believe me, I've read a lot of literature, and there's a lot of errors, a lot of crazy assumptions of people in the mining industry how to describe this layered approach in such a way that could be used in, for example, CFG code. Another approach, here's another example of approach. The most simplified approach is to have a core, some reaction zone, and then there's a reacted shell on the outside. This reaction zone has a number of reactions in it, as opposed to one reaction. And the other one is, of course, sometimes these pellets, they're compressed. They take iron powder, they compress them into blocks or spheres or blocks. And some people have proposed a grain model where these little grains of the iron powder, they're compacted into pellets of some 10 millimeters in diameter, and they each of these is the shrinking core. So these are complex models of the process, right? And so there is, and if you try and simulate this in a short space of time, you want a flow sheet simulation, you're going to take a long time to get an answer. And so this is not a way to go forward. Right? It's the first thing you think about. The next thing is you need to get down to the furnace model. So that's now the pellet model. So the furnace model is that your solids are falling down in this way. They essentially form a packed bed. They fall quite slowly, but they do fall. For those you can imagine that if those you pack sugar in a tube, you pour the sugar in, it runs down quite nicely, like it flows like a fluid. And then the gas rises up. So you have to describe this counter-current reaction system. And of course, you have the pellet sub-model to describe that. And so there's of course, there are models out there. They've done some CFD on this. I've got some examples here. Here's some results from Well, you go back one step, the most complex model or most detailed model I can find in literature is by the French group, Nancy. Places we went to a couple of years back. They have done the reductor model, and I see someone smiling at me. But this is some results from that model. You can see that the different stages. There's the red is the product 100% of a species. The blue means it doesn't exist. So you can see the blue means that this has been consumed. The red is where it exists, right at the beginning. The solids come from the top. So this is the direction of the solid movement downwards. And you can see the appearance of this one there, and then the appearance of that one there in the red, and finally the iron down here. And the one thing you can see is the profile is more or less flat. There's a bit of a parabolic profile, the flow pattern for the solids. Now, more or less, this is the center. So that's the wall. That's the wall. That's the center over there. Mm-hmm. So you get that flow rate like that. So there's some profile, but in essence, it's this iron which is of interest to us. And there's some other things. That's the water profile, the hydrogen profile, and so on. And this is the temperature profile. Again, the temperature profile is very clean, will rise from low temperature to high temperature on the other side. So a few things to note. We'll go through a few things. Iron is what you want. The other thing is the hydrogen is in excess, typically three times molar ratio. And that is required to heat. The gas is the excess hydrogen needed to actually heat the solids. Otherwise, it doesn't heat up. If you run stoichiometrically, it doesn't get hot. It doesn't go. You need to have that excess in about the factor of 3 or more. Right. Profiles are reasonably sharp. At least you can see here. There's an iron profile there. If you ignore the other species, you can maybe say, well, it's just a one single reaction. Is maybe a guess in the right direction to get something going. The temperature of the gas, if you look very closely, the temperature of the gas always exceeds the temperature of the solid. That's with the reactions in the solids extracting heat out of the gas. So it always lies below. So your results must replicate that in some respect. And the big hurdle is there's no data. It's very hard to get data of this nature. And there's no experimental verification. There's no real hard numbers on this actual simulation or measurement for a real furnace. You can't get a temperature profile. You can't get those kinds of things with some experiments on the single particles. So that even though these results are as comprehensive as can be, there's no validation. And so this is the only knowledge we have about the internal functioning, at least the first guess. So the way forward we've taken is a lot of approximations in this model, and for a first phase model, we don't want, let's make it quick and easy to work with. So let's use a quick answer. Let's make this into a flow sheet. So we decided just to follow the simple traditional textbook approximation. We have a shrinking core model. There's your iron unreacted oxide. There's the iron film over here. There's an instantaneous reaction at that point over there. And then you have a mass transfer resistance and a gas film resistance, and you form the classical 3-layer model, shrinking core type model, and you can do the maths of that. It's in every textbook in engineering. So this represents the simple conversion. It contains the gas film coefficients, the diffusion coefficient, and reaction rate constant. So you have 3 different zones of mass transfer, or conversion, or change. And so the time there is this represents the time for complete conversion in terms of this model. It's not this approximation. I won't go through those now. There's too long list to go through. But and this T here would be residence time in a stage. And we consider tanks in series approximately. So we divide up the whole column into tanks like this, much like a distillation column, phase of distillation column. And each of these we consider to be a well-mixed vessel, at least for the gas phase. And we'll talk about that in a minute. So the gas phase, we assume the well-mixed. Solid phase, the solids move through the gas phase. So we assume the gas phase is constant composition, and the solids move through that with a certain residence time. And then you can apply the model. Now, the problem with this model is that you have to apply for this stage, for example, here, this is some text over there. So the residence time refers to this time for complete conversion refers to the conditions inside this chamber and not from zero conversion. So this type of complete conversion is based on the conversion entering and the conversion leaving and the conditions inside this chamber. And so you have a different equation for every single stage, right? And you can solve this, so if you do the maths, so it's a cubic, you can solve it sequentially, and you can pose the condition that the conversion will keep increasing, and you can solve it for all the stages very nicely. Right? You can get into a solid phase Moll balance like that. It's very easy to do that. And if you then classical rate engineering, you have a overall reaction rate based on the solid volume, as you would call it, as an overall reaction rate. The nice thing is you can link the overall reaction for the stoichiometry, reaction stoichiometry, to the conversion that you've calculated. And then you can, the gas phase Moll balance, which is that one there, that common term, eliminates the reaction terms in terms of conversions per stage. So you don't have to know what the reaction rate is. You just use the conversions you calculate. They represent the overall rate of the solid phase. And of course, we can, going forward. Yeah, and then on the back. And we have energy balance as well. We recognize that the solids and gas temperatures are different. So we do energy balance using heat formation, formation balance. We cover the film heat transfer boundary, and there's the species flowing across the film, molecular movement. And we do one for the solid phase, we do one for the gas phase. And then we have basically in the end, we have 5 unknowns per stage, like the mole fraction of water, hydrogen, total flow rate, temperature, and of the solid and the gas, 5 variables per stage. And given an initial guess of all these 5 species, we can calculate the conversion. So we can implicitly calculate conversion, and we can solve this for stage by and because they're countercurrent. You have to solve this simultaneously. You can't solve stage by stage. You can't solve from stage 1 to stage 20. You have to solve the whole thing or simultaneously, make it done quite easily. Create a vector matrix arithmetic. Use science as a platform. We used to do vector arithmetic calculations. It's quite, performance is quite good, and we've done that. All right, and then of course we decided, okay, let's try and make this Cape open combined. Let's see how we can make this port this into cocoa. The cocoa, there's have to be the solid phase reaction, essentially what's happening here. So we basically create a little database, just simple compounds that we had these two solids with hematite and iron in the database, and then of course the gases. We made a custom one just for those two for it to run like that. We going through a reaction, overall reaction, the hematite to iron reaction. Then we form the properties. So we make enthalpy calls to T using the Scilab interface. The gas film properties, enthalpies for the gas film, densities, conductivities, and so on. And then the solid phase properties in the same way. So we get the properties from the database, and these are some results we get from that. You can just do an idea. This is 30 stages. You can solve 100, 200 if you like. 30 stages. It takes a second or so to solve quite quickly. At the top is your hydrogen concentration. The hydrogen flows goes in this direction. So this is coming in there and going out there. Your solids are coming in here and going out there. This is an example of what happens. And you can see it's about 3-to-1 ratio of hydrogen to solids, Moller. And here the temperature profile for the solids are coming in cold. There's the solids flowing in this direction. The solids are heated by the gas. And on the top here, the solids come out. There, the gas comes in hot, about 800 there. And yeah. But this end is the heating's down this end, huh? And if you don't have 3-to-1, if it doesn't get hot, it doesn't react. It simply won't react. So that we can make it, we can write it in the side of the unit operation. It works quite easily. It can be solved independently. And then we took this unit operation and imported it into cocoa. We had 2 targets. If we take the economic study, we had 2 targets, and the 2 targets were this. We wanted a surrogate model which doesn't have the unit operation in it, but gives the right conversion and the right energy footprint. So the right output streams, almost the same temperature, the same properties. So I built this little fixed conversion unit, which does the conversion. And because it's counter-current, you can do some funny things with you take the product gas and exchange the inlet gas and also other checks and balances to exchange all the heat in the system to deliver the outputs that you want. And I'm not going to read through all these small rules and checks I put in place, but the point is I can build a unit that replicates the unit operation without the knowledge of the size. simply getting the energy footprint. And then I then compared this to the unit plugin. I created a Scilab unit operation. Here it is in Cocoa with the same feeds, same everything. And we connected my input output streams in a counter-code fashion, gas in, solids in, gas out, solids out, there it is. And then this thing runs quite happily as a unit operation within the Cocoa. So this would be embedded unit, and it would have a size, you could respond to changes in flow rate, and we have nice things, so you could use it in the flow sheet configuration. And just to show, I've just summarize the numbers. So this is the surrogate model on top here. With the outputs, that's the output temperature over there, with the ins and output temperatures. They compare not perfectly good, but they don't have 10 degrees, 23 degrees out from the other ones. I haven't investigated why. I'm not. Mass balance is spot on, of course, sense the whole plans now. Okay. But we're able to do this. We're able to have both energy footprint and a proper model which responds to size, at least in the first principles working. I'm using the Cape Town tools. And the question is, what next? Well, there's some refinements I can still do. I haven't done enough. Some performance issues to address. And of course, the next job is to use this in the technical study for the hydrogen ion processing, which is what the other group or the ones that was interested in. And I've saved you time. Thank you very much.